in those regions. Yep, the upper function on the left, where that yellow highlight is 5 sin of 2x, the red function. And then the upper function on the right is the 5 sine of x, the blue function. And so we're subtracting them both in each case, but the order in which you subtract them makes a difference. So we have to make sure that's all good and groovy. Okay. So next is we're going to put those all together and actually do the work to make that happen. So if you're okay with those areas, we have to find the intersection as well. So when we get the intersections, when you're setting up to find those intersections, it's always about when the two equations are equal. So it's 5 sine of x, and I might need to go to another page for this. I want to know when it's equal to 5 sine of 2x. And that is the idea of finding an intersection. When two equations are equal is always about setting them equal. And so what we're going to do is set them equal and solve for x, because the x is the intersection thing we need. That's the a and the b that we need for our two. And there are multiple solutions. What you're going to find out is that we're going to have a lot of solutions, but we're only interested in the solutions that fall in our graphed region 0 to pi. So we're not looking for every possible solution. There's going to be a bunch of them. Sorry for the wind. So it's, man, really kicked up. But we're going to just solve this. We can divide both sides by 5 and effectively cancels these two from each other. And then you get sine of x is equal to sine of 2x. Now this takes a little bit of know-how in the trig world, because when does the sine of x equal sine of 2x? And knowing a little thing about the unit circle, that's kind of how I look at it. Or you can look at a graph of both of these if you know something about that, which would be helpful as well. But I'm going to just think about my unit circle. I know that sine is the y-coordinate on the unit circle, the height that goes there. And so if I'm looking for two places, I need an angle where if I double an angle, I get the same height value as if it were the same angle itself. And so the first example that comes to mind is pi over 3. Because pi over 3 is 60 degrees, it's that angle right there. The sine is the height, sine of pi over 3. The actual value of it I can tell you in a minute, but we just need to know what value of x. If I double pi over 3, you get 2 pi over 3. And 2 pi over 3, which is right here, has the same height as pi over 3 on the unit circle. That means they're equivalent in that location. Okay, so that height, they're the same distance from the x-axis up, the same y-coordinate. So an x that satisfies this particular equation, pi over 3, so that if I put pi over 3 in for x, and so boom, a little arrow right here, if I put it in there, if I double pi over 3, I get 2 pi over 3. But if I put pi over 3 in this one, basically I'm looking at the sine of pi of 3 equals the sine of 2 pi over 3, and they have the same value. So pi over 3 is our first x value that works. The other one on our interval 0 to pi is pi itself, because when I take pi, which is right here, okay, here's pi, if I double that I get 2 pi. They have the same height. They're both 0 units up and down from the x-axis. They both have a value of 0. So the two x's, and when we're thinking of trig, x is when it's the input inside here, we're thinking of an angle on the unit circle. So the solutions are x equals pi over 3. That works, because when I double it, I get the same sine value. And the other solution is x equals pi, because when I double that, I get the same sine value. So they are my two solutions. They are my a and my b. So those are the two x's that satisfy that condition. And so if I put those in here as a and b, I can erase these and we can go about integrating this stuff. So this one becomes pi over 3. This one over here becomes pi over 3. Right here. And then the top one, b, this is our pi, our endpoint at the end. So this is pi. So if you know how to set those up, you can obviously type it into Wolfram Alpha and get the whole solution to it, but of course it has to be done by hand, and so I'm going to copy and paste this if I can. I'm trying to. See if this works in this solution. Sometimes it works and sometimes it doesn't. So let's see. Copy that. Let's see. I don't know. Made a cool lasso. Didn't really do anything. Oh well. Maybe it didn't work. Let's see. Did that do something? Nope. Well, so much for that. But we'll figure out how to make that happen and put it on the other side. Used to be I could just grab it and make it paste somewhere. Oh well, we'll go to the next page. So if I can add a page below. And sure, ruled paper, that works for me. Come on, let's go.